Okay, good afternoon, everyone. So I'm going to present those results that were obtained in collaboration with Volker and Latifa and recently published in Nature. So you've already heard about generalized Proton distribution yesterday in Marcus' talk and also in Charles' talk. So I'm going to focus on the aspect of gravitational physics. So first, let me say a couple general things about confinement. We all agree on the definition of confinement is the idea that there is no net color charge in asymptotic states. In other words, hadrons are singlet under SU3, but the question is what is the confinement for the mechanism for confinement? For heavy quarks, I think we also all agree that there is a linear growth of the static quark-antiquark pair potential. This is seen in lattice QCD. This can also be computed in non-relativistic QCD. But the question is, what is the mechanism for light quarks, such as U and D quarks? So Vladimir Gribov made a proposal that the real mechanism was due to the analytical properties of the propagators in the infrared. So if we look here at the mass as a function of momentum, we have some lattice calculation and also some calculations that were performed within the Dyson-Schwinger approach that would correspond to the inflection point here at low momentum. Gribov's calculations led him to the following criteria. If you take a point-like nucleus, the vacuum is unstable against the propagation of such a state with charge above 137. He then went on to calculate corrections for finite size of the nucleus and found the value of 180. Now, he repeated the same calculation with all the glory of QCD and found that the number here was, first of all, easy to remember, but also very small, 0.137. So if you look at this quantity here, alpha over pi for QCD as a function of scale, you can see that it definitely goes above 0.137 in the infrared. Most of the points here, by the way, come from class. There's also a curve here that was obtained by Strandbrowski and collaborators using light front ADS QCD. And in this scenario here, the quark and gluon chiral condensates themselves are confined. Now this has consequences in cosmology, namely for the cosmological constant. As you may know, the calculation of the cosmological constant in quantum field theory fails by 170 orders of magnitude. So this would resolve that particular problem. Okay, so all of this, I guess most of you are familiar with. I will remind that this mass function here, the generation of mass in Young-Mills theory carries a $1 million prize by the Clay Mathematical Institute. It really has to do with the definition of what Young-Mills theories are. And the best known approach to address those questions actually has to do with a very surprising link between gravity and QCD, so I will say a couple of words about this. There is a very fundamental sense in which a graviton can be understood as a pair of vector bosons. If you calculate amplitudes for gravity within the quantum field theory framework, you will find that they are actually the square of Young-Mills amplitudes in the so-called color kinematics duality. The classic reference for this is gravity as the square of a gauge theory, which was published in 2010. And this idea is crazy enough that it might have eluded Richard Feynman. Understanding the deeper origin of this duality is, of course, at the heart of string theory. In string theory, a graviton, which is a closed string, is naturally thought of as a pair of vector bosons which are open strings. The duality between gravity in the bulk and QCD, also called the holographic principle, is currently the all-time most cited high-energy physics publication. This is, of course, Maldacena conjecture, currently with 13,000 citations. So with this perspective, gravitational form factors for QCD bound states are observable of choice to test these dualities. So the gravitational form factors, they're related to the energy momentum tensor here. Of course, the object that naturally couples to the energy momentum tensor is the graviton, but gravity is too weak to produce any sort of count rates in our detectors. So again, a graviton can be thought of as a pair of vector bosons. And that's the idea behind Xiang Dongji and Maxim Polyakov publication, to use a process with two photons to measure the energy momentum tensor. And hence we arrive at the idea of generalized parton distribution. There's a photon in the initial state. There's a photon in the final state. And in the Bjorken regime, the process factorizes with those objects here the generalized parton distributions, which are really Fourier transform along the light cone of those bilocal operators here. Not in passing that we can replace here the photon with another vector boson, such as, for instance, a rho, an omega, or a phi. At leading twist, there are four chiral even GPDs, H, E, H tilde, and E tilde, depending on whether we flip the spin of the quark or whether we flip the spin of the nucleon. In this talk, I'm going to concentrate on the GPD H. So in more details about the energy momentum tensor, there are three gravitational form factors, M2, J, and D1. J is the famous angular momentum distribution form factor that appears in the G sum rule. And it's related to the second Mellin moment of the sum of the GPDs H and E. There are two other form factors, M2 associated with the mass distribution and D1 associated with the force and pressure distributions inside the proton, and they're related to the second Mellin moment of H alone. And we see here on this graph the distribution of pressure weighted by the factor R square. The reason it was weighted by the factor R square is because there is a stability condition that the integral of R square times the pressure should vanish since the nucleon is a stable object. This particular curve here was obtained by Maxim Polyakov and collaborator within the Carroll quark soliton model, and it exhibits a positive quark core with repulsive forces and a negative pion cloud, which we claim is related to confinement. So in order to access these operators in the lab, we create a beam of virtual photon using an electron. There's another process, apart from deeply virtual Compton scattering, that contributes to this reaction is the Bethe-Heitler. And the two are indistinguishable, so they interfere at the amplitude level. And if you analyze an observable such as, for instance, the beam spin asymmetry here as a function of the angle phi between the hadronic and the leptonic plane, you will find that at twist 2, it has this characteristic shape, alpha sine phi divided by 1 plus beta cosine phi, where alpha is the imaginary part of this GPD combination. Well, actually, it's not a GPD. It's a Compton form factor, but it has this calligraphic shape. So the Compton form factor, its imaginary part is the GPD at x equals psi, and its real part is related to the principal part of this integral here along the 1 over x minus xi. Okay, so now I go to results that were published in 2008 from class for the beam spin asymmetry again. This is mostly sensitive to the GPD H. And you can see here in the insert integrated over the entire phase space the characteristic shape that I was telling you about, this alpha sine phi divided by 1 plus beta cosine phi. There are actual error bars on those points, but they are invisible at this scale. And now if we take these distribution as a function of phi, we fit them, and we want to look at this alpha, which is of interest here, as a function of t from 0 to 1.75 minus t, and in the q square x Bjorken plane. So you can see, in particular, compared with the Van der Hagen-Guichon-Guidal model that wasn't tuned on the data at the time, there is a fair agreement. And in particular, you can notice the change of slope as a function of X Bjorken. I'll say more about this later. We also made use of the unpolarized cross-sections, which we published in 2015. And you can see here again the points are compared with the pure Bethe-Reitler if there is no contribution from DVCS at all. So you can see that most of the difference in log scale occurs around phi equal 180 degrees. Okay, so a little bit more details about this X dependence of the alpha term. So it's plotted here for all the bins that we have published in 2015, 21 bins. Again, as a function of t, and you can see that the slope is much steeper at low x and much shallower at high x. And this is interpreted now. If you make the Fourier transform, it means that the partons at high x are located in the center of the nucleon. Or in other words, the partons at small x or the C quarks are located at the periphery of the nucleon. All right, so we performed a global analysis, a global fit of those data using a dispersion analysis framework. So in a little bit more details, all those asymmetries here, they were fitted with a parametrization for the imaginary part of H here. That parametrization was proposed by Dieter Müller and Krasimir Klimerici in 2010 in their own global analysis. We just reused the same form. And then we fit our unpolarized cross-section data by calculating the real part of the Compton form factor from an integral over this imaginary part of H and a subtraction constant, which is none other than the D term. And you can see here, again, a comparison between our points and the pure Bethe-Reitler. The local fits in individual bins given in blue, and the resulting global fit to our entire data set in red. So once we put all of this together, this is our result for D1 of T. So if you notice in detail, I was talking earlier about this large D. This large D is actually related to D1 by a Gegenbauer expansion. Okay, so the fact that this D1 of T here is negative is actually a very fundamental property which is related to the dynamical stability of a bound state. This quantity here, this is the first measurement of what can be considered a new fundamental quantity on the same footing as the mass or the angular momentum or the electric charge, actually. These first results here, they have been recently compared to a world data set calculation in a publication that's on arXiv by Maxim Polyakov and Peter Schweitzer. So our points here appear in purple, and you can see, again, a curve that corresponds to the dispersion analysis. Compared to other analysis, so the global fit by Krasimir Klimerici and Dieter Müller, the version of 2015, but also some lattice points, as well as a chiral quark-soliton model. And again, if you look into this publication, there is a table here that sets this new quantity on the same footing as the angular momentum, the mass, or the electric charge. So if we make the Fourier transform now, we can obtain a distribution of pressure, which is very reminiscent of the plot that I showed earlier from the chiral quark-soliton model calculation, with a positive core and a negative pressure at the periphery that provides a confining pressure. The pressure that we found is extremely high. It's 10 times higher than the core of a neutron star. Let me mention that we have a proposed experiment, E12-16010b, which will improve the R bars as shown on this plot here. Okay, so as a conclusion, we have presented a new perspective on the exclusive reaction physics. This is the first ever measurement of a gravitational form factor, and it opens a new avenue to test confinement mechanism. So it involves the partonic energy momentum tensor. Those are quite exciting time at the beginning of the 12 GeV high precision era. Let me mention that this will also be an essential part of the EIC program. Thank you for your attention.
So if you take a simple calculation of quark-gluon plasma, of the relativistic Fermi gas of light quarks, and calculate the pressure, it comes out to be about the same value that you measure in this. So it's probably no accident. It's if you think of it as a bag model, and you create a bubble in the vacuum, and you have the quark pressure inside. So, yeah.
Yeah, this number here can also be found directly, just if you use the mass of the proton and the size of the proton, you'll get roughly the same scale. So, yeah.
Any more questions? Let's thank our speaker again.